Well, hey there, welcome to another podcast. This one will be on thermodynamics. We're going to look at heat, disorder, spontaneity, all kinds of stuff. You'll need your calculator out, your brain, writing utensil, notebook, a smile every once in a while, that kind of stuff. Okay, let's go ahead and get started. We're going to first talk about the fact that energy is defined as the capacity or the ability to perform work. It is probably most often measured as heat. So we can state that heat and energy can have the same units. A lot of folks think that joules are a unit of energy and calories are a unit of heat. Well, they're both units of energy, and since heat is a form of energy, both can be interchanged. Joule is considered a unit that is a System International unit, SI unit, and calories an English unit. I'll explain what a calorie truly is in just a bit. So I want you to envision a tub that is filled with water at 35 degrees Celsius. Assuming that you have a cup that is at the same temperature as the water, I want you to dip a cup into the water and fill it. What's the temperature of the water in the cup? Well, as you think about it, you should think that, okay, the temperature of the cup, the temperature of the water are the same. I dip the cup into the water, it's going to have the same temperature as the water in the tub, meaning 35 degrees Celsius. Now, which amount of water, that's in the tub or in the cup, can melt the greater amount of ice during the same time? In other words, I put an ice cube in the tub and I put an ice cube in the cup of water. Which one will melt that ice first? You should say that the tub is going to melt the ice first. So, what we get from that is the idea that two substances that have the same temperature can have different amounts of heat energy because there is more of that substance. So, in these two examples, the tub water and the cup water, they both hold water that's at the same temperature, but the tub possesses much more heat energy because it possesses more water, a greater mass of water. Temperature is officially defined as a measure of the average kinetic energy of a substance. Do you recall from physical science, if you had it, what kinetic energy is? I hope that someone in here realizes that it's the energy of motion. You might recall that you learned in a physical science class that Ke, kinetic energy, equals 1/2 of the product of the object's mass and its velocity squared. So 1/2 mv squared equals Ke. Well, what that indicates to us is that if an object is moving at the same velocity, but we have more mass of it, then we can have a greater kinetic energy. So heat is defined as the measure of total energy that is transferred from one object with a higher temperature to an object with a lower temperature. It's a measure of the total amount of energy that's transferred. So we're looking at average kinetic energies of two different objects that differ, and that transfer of energy is considered the total amount of energy. Heat will always flow from higher temperature to lower temperature, or higher energy to lower energy. So when your mom tells you to close the door because you're letting all of the cold air inside, you could be really obnoxious. Pardon that would be something that a cat knocked over. Yep, you're used to this by now. You could be really obnoxious and correct her by telling her that in actuality, you're letting the hot air outside, and it only feels cold due to the lack of heat inside. In other words, the cold air from outside is never going to move in. The hot air from inside will move out. And in the summer, obviously, it's the reverse. So what we're going to do is measure heat in either the SI unit of joule, using an uppercase J, or with the English unit of calories, using a lowercase cal. A calorie is actually the amount of heat energy that's required to raise 1 gram of water by 1 degree Celsius. And what that means is if I had 1 gram of water, it's about a milliliter of water, at 20 degrees Celsius, and I wanted to raise its temperature to 21 degrees Celsius, I would give the water 1 calorie of heat energy. If I had 20 grams of water, however, how many calories would be required to raise its temperature from 20 degrees to 25 degrees Celsius? Get that calculator out if you need to. Think about that. 20 grams of water, and I want to raise it from 20 degrees Celsius to 25 degrees Celsius. You should determine that it would require 100 calories. It's a little dimensional analysis that you should do, meaning 1 calorie per gram degree Celsius, where your calories in the numerator, your gram and degree Celsius are in your denominator, times 20 grams times 5 degrees Celsius. Write it out. 1 calorie per gram degree Celsius times 20 grams times 5 degrees Celsius will equal 100 calories. You need to know the conversion factor for calories to joules and vice versa, so I want you to know that 1 calorie equals 4.18 joules. Thus, how many joules would be required to make the previous problem's change in temperature? So now you just have to do your dimensional analysis again, knowing that 1 calorie is the same thing as 4.18 joules, and the previous problem required 100 calories, so you should tell me that 418 joules would be needed to heat those 20 grams of water by 5 degrees Celsius. I want you to graph the data that's on the next slide. It shows 2 experiments data, and I just want you to do a rudimentary hand-drawn graph. Don't use a graphing calculator. I want you to think about what's going to go on your x-axis and what's going to go on your y-axis, and think about what happens as you look at this data. So just on your normal notebook paper, take a look at this slide, and I've given you the temperature and the time that it takes in seconds for 1 cube to go through this temperature range and for 8 cubes to go through this temperature range. So you can copy the data table. I want you to be able to come back and look at your data. Think about what your dependent variable is and what your independent variable is. What are you controlling? Remember, time is not always an independent variable. Once you've copied the data, you can make a graph with 2 lines representing 1 cube of ice and 8 cubes of ice. Just give them different colors, or make one solid and one dashed, something like that. You can stop the podcast while you do that. Then I want you to check the next slide. Alright, as you see on this, I didn't put any quantities. Again, I just wanted this to be a simple little know-nothing graph. You did put temperature on your x-axis, I hope. That is what you controlled. We controlled the temperature. We were looking at how long it took to go from 0 degrees Celsius up to, 100 degrees Celsius at different time points. So we recorded time. You should see that the lower line on this graph is representative of the 1 cube of ice, and the upper line is representative of the 8 cubes of ice, meaning it took a longer time for the 8 cubes of ice with the greater mass to go through the same temperature changes. Okay, so that's just getting you to think a little bit about graphing. Let's talk a little bit about specific heat capacity. It is represented in shorthand by capital S, capital H, capital C, or by just an uppercase C. You will see it both ways. I tend to use SHC. Most physicists use just C. It's defined as the amount of heat energy needed to raise the temperature of 1 gram of a particular substance by 1 degree Celsius. Should sound kind of familiar, And all pure substances, all elements and compounds, will have specific heat capacities. The specific heat capacity of a substance does change as the substance's phase changes, which means, for example, ice, water, and steam have varying specific heat capacities. I gave you the definition of a calorie previously as the amount of heat required to raise 1 gram of water 1 degree Celsius. Well, what that means is that the specific heat capacity of water is 1 calorie per gram degree Celsius, or 4.18 joules per gram degree Celsius. You really need to commit that one to memory. You're going to be using it quite a lot in the problems that you work out. So again, the specific heat capacity of water is 4.18 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. So what do we do with specific heat capacities? Well, if I have two substances with differing specific heat capacities, like water and aluminum, then the one with the greater specific heat capacity will require the addition of more heat in order to make its temperature rise by the same amount as the substance with the lesser heat capacity. Of water and aluminum, which one do you think has the greater specific heat capacity? Think about which one gets hotter more easily. The one that gets hotter more easily has a lower specific heat capacity. So you should think about it. If I have aluminum foil even sitting on a burner of a stove, and I have water in whatever vessel, I turn the burner on, which one am I going to be more willing to touch and be comfortable touching? You should say that the water is what I'm going to be more willing to touch. And what that means is that water has a higher specific heat capacity than aluminum. And again, remember, water's specific heat capacity is 4.18 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. Aluminum's, by the way, is 0.215 calories per gram degree Celsius. So significantly less than the 1 calorie per gram degree Celsius of water. And that means aluminum will get hotter with less energy than water. So think about this. Of silicone or iron, which one has the greater specific heat capacity? Think about the silicone oven mitts that are pretty popular these days. And think about a cast iron skillet. Which one are you going to say you'd like to touch after they've been supplied with some energy? You should indeed say that the silicone is the one you would prefer to touch, which means that it has a greater specific heat capacity. I've given you on this slide an equation that you'll use quite a lot, and it is that we can measure a change in heat by equating it to a change in temperature, which is final temperature minus initial temperature, times the mass of the substance, times that substance's specific heat capacity. Again, you'll make use of that equation quite a lot. It does involve just dimensional analysis, by the way, so if you don't have to remember the equation if you can just work through the dimensional analysis. But in a physics class, for example, you'd be given this equation most likely. All right, what you see on this slide is known as a heating curve, and this is the heating curve for water. On the x-axis you have heat, in this case measured in calories. On the y-axis you have temperature measured in degrees Celsius. I've given you segment notations on here and told you where ice is, where ice and liquid water exist together, where liquid water is, where liquid water and vapor exist together, and where you have just the water vapor. So go ahead and copy that one down. There are no values on the x-axis at this point. I'll give them to you on the next slides, meaning what values I would like you to just perceive. But I would like you to look at the slide, copy it, so that you can understand what I'm telling you on the next slides. If you need to stop the podcast and give yourself time to record it, please do so. When you're ready, go to the restart the podcast and it'll start with the next slide. So segment BC has a value of 80 calories per gram. It's called the heat of fusion if the conversion is from solid to liquid. In other words, the amount of heat required to change 1 gram of ice into 1 gram of water at the melting point is the definition of the heat of fusion. The heat of solidification is also 80 calories per gram, and it's the amount of heat that has to be lost by 1 gram of water to turn into 1 gram of ice at the melting point or freezing point. Remember that melting and freezing point are the same thing. They're the same temperature. Segment DE has a value of 540 calories per gram. Notice the length of segment BC compared to the length of segment DE. Segment DE is called the heat of vaporization or the heat of condensation. It depends on which way you're going. If it's the heat of vaporization, then it's the amount of heat that must be absorbed by 1 gram of water to convert itself into 1 gram of vapor or steam at the boiling point. Going the other way, if 1 gram of steam is losing 540 calories, then it will convert to 1 gram of water at what's known as the condensation point. So, do you recall from biology that sweating is known as evaporative cooling? If not, it is. It's known as evaporative cooling because as you sweat and that water sitting on your skin vaporizes, it indicates that you are losing energy, that water vapor absorbs energy to be able to vaporize. Well, where does that water vapor absorb the energy? Yep, it takes it from you, which means you're left with less energy, and that means you're in turn cooler. Continuing to look at this heating curve, point G has a value of 0 degrees Celsius. It is the melting point or the freezing point. They are the same temperature for any substance. A melting point and freezing point are the same thing. Point H has a value of 100 degrees Celsius, and it is the boiling point or the condensation point. Again, they are the same thing for a substance. And notice that there's no change in temperature at these points, per se, until the phase is completely changed. Once that phase change is complete, then if we continue to supply more energy, the temperature will go up. Okay. In order to help us better understand this, we have measurement of heat that needs to occur. And to measure heat, we use a process known as calorimetry. It's literally the measuring of heat, the measuring of calories. There are 2 types of calorimeters. One is known as a constant pressure calorimeter, also called a coffee cup calorimeter, because yes, you can use coffee cups. I tend to use styrofoam coffee cups to be able to keep the pressure constant and reduce the loss of heat. And there are constant volume calorimeters, also known as bomb calorimeters. A bomb calorimeter is usually used when you have some sort of combustion occurring. When we look at biological calorimetry, we pay attention to the nutrients that we take in and the number of calories that are associated with each one. We'll spend more time on this in a subsequent lesson, but I'm just introducing it here so you start to think about how all of this kind of relates. The nutrients we worry about taking in each day are carbohydrates, proteins, and lipids. Those are our primary sources of our energy or calories. And then, of course, we need to take in water, vitamins, and minerals. It's carbohydrates, proteins, and lipids, again, that we get our energy from. So I'm just going to ask you to note at this point, so you can work a few problems, that 4, this is not a minus sign, that is a bullet, that 4 kilocalories per gram are associated with carbohydrates. Meaning, if you have 1 gram of carbohydrate that you take in, you can break that down into 4 kilocalories of energy. And remember, a kilocalorie is not the same thing as a calorie. That means that there are 1,000 calories in every 1 kilocalorie. Well, 4 kilocalories per gram translates into 17 kilojoules per gram. Proteins have the same energy content. 4 kilocalories per gram or 17 kilojoules per gram. It is lipids that we end up getting a lot of energy from. It takes a lot of energy for us to break it down. 9 kilocalories per gram or 38 kilojoules per gram. We will use either kilocalories per gram or kilojoules per gram as I've given these to you. You'll need these values for some future problems. Okay, let's look at what's known as the heat of reaction. When we have a chemical reaction that takes place, there's always an absorption of heat or a release of heat. If the energy is absorbed by the reactants during a chemical reaction, then the process is known as an endothermic reaction. If the energy is released by the reactants during a chemical reaction, then the process is known as an exothermic reaction. If it is absorbed, then the energy itself can actually be written as a reactant. If the energy is released, then the energy can be written as a product. So all chemical reactions will have what's known as a delta H with RXN, which is short for reaction, as a subscript. Some variations upon that theme are the heat of formation, delta H, and then formation, often abbreviated as delta HF. It's the amount of heat that is absorbed or released during the actual making of a pure substance under specific temperature and pressure conditions. You don't need to know these, but specifically 298 Kelvin and 1 atmosphere of pressure. You'll learn about pressure units, and the next big unit that we talk about will do gases and gas laws. Another deviation is the heat of solution, which is the amount of heat that is absorbed or released when a pure substance dissolves in a solvent. So you'll actually do a lab where you calculate the heat of solution of sodium hydroxide in water. You'll do that in a few weeks. And another one is the heat of combustion. It's the amount of energy that is released. Notice I'm not saying absorbed or released, because it's always released when a substance combusts or reacts with oxygen gas to form carbon dioxide and water vapor. You definitely need to remember how to write balanced equations, in particular for this one, how to do my little cheating thing of putting a 2 in front of the hydrocarbon to get your combustion of a hydrocarbon to balance. Remember, that was my cheating method, because you could always go back and reduce if you needed to. So a heat of reaction, regardless of whether it is just a plain Jane heat of reaction, whether it's a heat of formation, a heat of solution, or a heat of combustion, is always a part of the stoichiometry of a reaction. So I've shown you on this slide that the heat of combustion of methane is 803 kilojoules. And I've shown you the balanced equation. And notice I've slipped in there that 803 kilojoules are also a product. And that allows me to look at this stoichiometry and say, I'm reading from left to right, that when 1 mole of methane reacts with 2 moles of oxygen, it will produce 1 mole of carbon dioxide, 2 moles of steam, and 803 kilojoules. That's part of the stoichiometry now. Well, what if I had 5 moles of methane present? Well, it's stoichiometry. You just set up dimensional analysis and you say 5 moles of CH4. You look at that balanced equation, and now the 803 kilojoules are part of the balanced equation just as any of the other substances are. And you say to yourself, okay, 5 moles of CH4 times 803 kilojoules over 1 mole of CH4. That's what I know from my balanced equation. And go ahead and calculate that. You actually should get 4,015 kilojoules are present, or needed rather, to completely react 5 moles of methane. So we'll do some more work with stoichiometry and heat as we get into your practice problems. So what I'd like for you to do, you have several practice problems here. Copy them, work them. You'll be able to check your work on my sheets that I have out for you. And then we'll need to do some more stuff with energy. So I just need you to, I guess, stop the podcast so you can record your problems. I'm not going to guide you through them. But do pay attention to my little pssts that I put here. You can work together as usual, just keep the noise level down, but I do want you to work each of these. Alright, so here's number 1. Stop the podcast, restart it when you're ready to go to number 2. And number 2, you need to think about a swimming pool. I didn't say on here that it is a rectangular prism, but it is. Again, stop the podcast, copy it, turn it back on as you need to. Number 3 involves a reaction of butane. Again, think about how to write a complete combustion reaction. Think about what I told you a heat of combustion would always be. You hear a mooch kitty in here. He's liable to talk and jump up on me. Stop the podcast so you can copy it. Number 4 requires that you go back to your data on food that I gave you and use the table that's on the next slide in conjunction with that data on carbohydrates, proteins, and lipids that I gave you. Notice I am specifically asking for the number of kilojoules provided by the fat in one serving. When you've copied this, go to the table on the next page. And in this table I've given you the food amount, the kilocalories, the carbohydrates in grams, the proteins in grams, and the fat in grams. And that enables you to calculate your kilojoules. Alrighty. Number 5, I've asked you, is more energy released when 428 grams of hydrogen or 428 grams of isooctane react with an excess of oxygen? That excess of oxygen just means that the oxygen is the excess reagent and the hydrogen and isooctane in their respective reactions are the limiting reagents. Make sure that the reactions are balanced before you start. It looks like I balanced them for you, but check them. You need to always do that. And yes, I probably did balance them. But again, this involves stoichiometry. On the next slide, you'll find your answers to these 5 questions, and then I'll get started with the remainder of the podcast. I'm about halfway through. So once you're finished working these problems, again, you can check them on my yellow pages, and then we'll get started with the next section of this podcast. And we're back to learning some more stuff, so let's take a look at what activation energy is. It's defined as the energy that reactants must get in order to turn into products. It can be represented by an uppercase E with the subscript of a lowercase a. If you took physical science, then you probably learned activation energy is the top of a hill, and once you're at the top of the hill, then you can roll down the hill and have a reactant turn into product. So as we look at this graph, we have reaction progress or time on our x-axis, and we have energy in kilojoules on our y-axis. Our reactants, notice, start out with some amount of energy. They increase their amount of energy to reach the top of the hill. The top of the hill energy subtracting the reactant's energy gives you the activation energy, or the difference between the top of the hill and the starting point is your activation energy. Once you're at the top of the hill, you're known as being an activated complex. And once an activated complex exists, then they can be turned into products. In this particular example, the products have lower energy than the reactants. And if I were to calculate an energy of reaction, I would take product energy minus reactant energy. Now look at those, not values, but look at those lines and where they are. If I did product energy is less than reactant energy. What would the sign of my delta H be? You should say that it is going to be negative. A negative delta H means that it is an exothermic process. And yes, you should be writing that down. I want you to think about what an endothermic process would be. Draw a little graph like this, yet make it endothermic. And what you should see is that your products have more energy than your reactants. You still have an activation energy, and you still have an activated complex that's higher than the energy of reactants or products. But your products have greater energy than your reactants. So your delta H will be positive, and that indicates it is endothermic. I'll review that with you in class. I just haven't drawn it here. And on this slide, we see that we can catalyze a reaction. A catalyst is a substance that will increase the rate of reaction, or how quickly a reaction takes place. In this particular graph, the blue line represents what a catalyst will actually do. Its job is to lower the activation energy so that the reactants can turn into products earlier than they would otherwise do. Notice that the blue line stops earlier on in the reaction progress than the pinkish, whatever color that line is, stops. So the products got formed a little earlier. Some examples of catalysts are the enzymes in our body. For example, most of you have learned about salivary amylase. It's the enzyme or protein that lives in your saliva that initiates the breaking down of carbohydrates. It would take you a lot longer to break down the food that you put in you without these enzymes. There are all kinds of other enzymes, I'm just not going to go over them. And you wouldn't be able to get the energy quickly enough. So our body definitely needs them. A non-biological enzyme example is that you can have platinum little ball bearings in what's known as a catalytic converter within your car. The job of that catalytic converter is to convert your exhaust gases into less noxious fumes, and do so more quickly. Enthalpy is a quality that can be equated with heat as long as we are at constant pressure. Enthalpy is the same thing as heat as long as we are at constant pressure. It's represented by an uppercase H. So as I've been giving you delta H here and there, I'm really giving you change in enthalpy. We'll look at a concept known as Hess's law to help us calculate some changes in enthalpy. And Hess's law tells us that there are multiple ways to find a delta H of a reaction. Using Hess's law, we can understand that when we go from a set of reactants to a set of products, the change in enthalpy is always the same, regardless of how we get there. If we do it in one step, it'll be the same as if we do it in 10 steps. It doesn't matter how you get there, you're going to end up in the same place with the same amount of energy change. In Hess's law problems, there are two things that you need to remember. There are two ways to manipulate your steps in order to get your overall reaction. This doesn't make any sense right now, but it will. If a reaction is reversed, if you manipulate it and reverse it, then the sign of its delta H is also reversed. If the coefficients in a balanced equation are multiplied by an integer, then the value of delta H is multiplied by that same integer. You'll have to just analyze your steps and your overall reaction to determine what needs to be done. So we're going to consider this reaction of 1 mole of nitrogen gas reacting with 2 moles of oxygen gas to make 2 moles of nitrogen dioxide gas. As we look at that reaction, our assumption is that, okay, we take a mole of N2 and 2 moles of O2, boom, slam them together, we get 2 moles of NO2. Well, it doesn't necessarily occur in that manner. In fact, most often this reaction occurs in a few steps that we can add together. These steps are known as elementary steps. Again, we add them together to get this overall reaction that we see on this slide. Some plausible elementary steps for that particular reaction on the previous slide are that we can have a mole of N2 gas react with 2 moles of O2 gas to make 2 moles of nitrogen monoxide gas. I've given you the delta H for that reaction as 180 kilojoules. Every time that reaction occurs, it absorbs 180 kilojoules. How did I know it absorbed it? Because it's a positive value. It means it's endothermic. And a second step is that 2 moles of nitrogen monoxide react with 1 mole of oxygen gas to make 2 moles of nitrogen dioxide. Its delta H is negative 112 kilojoules. That means it's exothermic, or it spits out 112 kilojoules every time that process occurs. How do I know it's negative? No, I didn't mean to say that. How do I know it's exothermic? It's because it's negative. Alright, so what we will do to make this work is take A and write it as it sits. We will take, it should say B up there, so I'm wrong on my slide, I'm sorry. We should take A, write it as it is with its delta H at 180 kilojoules, and take B, not C, there was no C, and write it as it is. I try to kind of line up my yield signs. Notice I didn't do a great job on this, but I try. Alright, I then add those 2 elementary steps together. And when I do so, I will get a mole of N2 gas plus 2 moles of O2 gas. Notice I had 2 like O2s, plus 2 moles of NO gas, yield 2 moles of NO gas plus 2 moles of NO2 gas. Now at that point I need to combine like terms as I did with the O2s, but I also can get rid of like terms that are on opposite sides of the yield sign. So what do you see that I can get rid of? You should be saying the 2 moles of NO. So since I have 2 moles of NO on the left and 2 moles of NO on the right, I get rid of them. Had I had 2 moles of NO on the left and 14 moles of NO on the right, I would have gotten rid of the 2 moles on the left and be left with 12 moles of NO on the right. It works just as you think it does. While I added my elementary steps, I'm also going to add my delta H's. I didn't change either reaction, which means I didn't change either delta H. When I add 180 kilojoules and negative 112 kilojoules, I get a positive 68 kilojoules. When I cross out my 2 moles of NO and clean it up, I actually get my overall reaction that I presented you with, and I see that its delta H is positive 68 kilojoules, which means it is an endothermic process. So let's try another one. I've given you graphite converts to diamond. I want you to use the enthalpies of combustion for graphite and diamond as your elementary steps and calculate the delta H for the conversion of graphite to diamond, stating whether it's endo or exothermic. So this is our overall reaction. Graphite converts to diamond. Your possible elementary steps that you will use are as indicated on this slide. Graphite reacts with oxygen gas to produce carbon dioxide gas. The delta H is negative 394 kilojoules. And B, diamond reacts with oxygen gas to produce carbon dioxide gas, and its delta H is negative 396 kilojoules. So the way that I teach folks to do Hess's law is to take one substance in the overall reaction at a time. I look at the overall reaction and I see that graphite needs to be on my left side and I need 1 mole of it. So as I analyze it, I'm going to write elementary step A as is because I have 1 mole of graphite on the left side. The only other substance I need for my overall reaction is a mole of diamond, but it needs to be on the right side. So I'm going to flip B. And when I flip B, it will read that I have a mole of CO2 gas yields a mole of diamond plus a mole of O2 gas. Remember, if I flip the reaction, I have to flip the sign of my delta H. So the delta H will then be positive 396 kilojoules. So let's look at whether you got that written correctly. And as you look at this, you see that you have on your left side in your summation, graphite plus O2 plus CO2 yields CO2 plus diamond plus O2. Well, lo and behold, I get to get rid of the oxygen on each side and the CO2 on each side, and that leaves me with graphite yields diamond. Get my delta H by adding my delta H's, and I will get 2 kilojoules. That means it's endothermic, and that means it has to absorb energy. Would you agree that graphite has to absorb energy to turn into diamond? I hope so. Okay. Another way to find a standard, a delta H is to use what's known as the standard heat of formation. And the equation for doing so is that your delta H will equal the sum of your heat of formation that is standard for your products minus the sum of the standard heat of formation of your reactants. Your Chemistry 1 book doesn't give you a good chart on this, so we're going to use the appendix in the Chemistry 2 textbooks. I just ask that you put them back when you're finished. The zoomed all text gives you a nice several pages worth of thermodynamic data. Little note, all elements in their natural states will have a delta HF standard that is 0. So we're going to go through a similar reaction to what we already did. Take a guess. We'll start with the nitrogen and oxygen reaction. And we're going to find the delta H using delta HF standard values. So we've already found the delta H of this reaction using Hess's law. I'm just showing you another way to find a delta H of a reaction. So I want you to look up in the Chemistry 2 textbooks the delta HF of N2, O2, and NO2 gases. Phases are very important. Notice that the units are kilojoules per mole, so you do have to consider how many moles of a substance you have. And I show you on the next slide exactly how I want you to write it out. And yes, I want it written exactly as you see it. So I first start with my products. I only have one product. It's 2 moles of NO2 gas. I look up its value in the chart and I see that it's 34 kilojoules per mole. Notice I've multiplied 2 moles of NO2 times 34 kilojoules per mole. My moles will divide out. They are my only products, so I have nothing else to do for my products. I'm then going to subtract the sum of the delta HF standard values of my reactants. Well, do you recall I told you an element in its natural state will have a delta HF standard of 0. So 1 mole of N2 times 0 kilojoules per mole, put that in parentheses, plus 2 moles of O2 times 0 kilojoules per mole, put that in parentheses, put the whole thing in brackets. And yes, I expect you to write 0 kilojoules per mole. And that means I will have 68 kilojoules minus 0 kilojoules, and I therefore get 68 kilojoules. The reaction is endothermic, and it happens to be the same delta H I got using Hess's law. I know I'm tricky, huh? Alrighty. I want you to do the same process using delta HF values for the reaction that converted graphite to diamond. So look up the delta HF values of the graphite and diamond and calculate the delta H, and you should find it to be the same value you got in the Hess's law problem. You can stop the podcast, give yourself a little time to do that. So now that you've finished working with enthalpy, we'll throw in a little tongue twister here, entropy. Entropy sounds like enthalpy, but they are very different. Entropy is a measurement of the amount of chaos or disorder that is present in a substance. As a chemical reaction occurs, the entropy of the reactants and products isn't guaranteed to be equal, their level of disorder. So we can have an increase in entropy or a decrease in entropy. Entropy is represented by an uppercase S, and a change in entropy is represented by delta S. If delta S is positive, it means that entropy is increasing. If delta S is negative, then entropy is decreasing. So, some little tips on figuring out what entropy will do is if you have more moles of products than you do reactants, entropy usually increases. If vice versa is there, you have fewer moles of products than reactants, then entropy will usually decrease. If you have a phase change that goes from more organized to less organized, entropy increases. In other words, going from water to steam, entropy will increase. If I did the opposite, went from steam to water, I would get more organized, or entropy would, if I go from water to vapor, I'm getting less organized, which means entropy increases. If I go from water to ice, I'm getting more organized, which means entropy decreases. If delta S is positive, entropy increases. If delta S is negative, entropy decreases. We hopefully have that straight by now. Alrighty. To calculate a change in entropy, you use the same sort of equation you used to calculate a delta H, but you use standard entropy values. You'll find them on the same appendix pages in the Zumdahl textbooks. So the sum of the change in entropy standard of your products minus the sum of the change in entropy standard of your reactants equals a delta S. That is Lyndon, you hear, growling at Mooch as they play. They need attention desperately because I've been in here recording this for quite some time now. So, he's just talking. He just reached up and scratched his nails on the wall and made a lovely screeching sound, kind of like you hear on a chalkboard. And now he's talking as he walks off. Woohoo! Alrighty, we're going to find the change in entropy of the N2 and O2 reaction and think about what it is before we actually calculate it. We're going from 1 mole of nitrogen gas and 2 moles of oxygen gas to 2 moles of NO2. How many total moles do you see on the left side? You should be telling me that you see 3 moles total on the left side, going down to 2 moles on the right side. What is that going to probably tell us is happening to the entropy? You should tell me that it should go down, that it should be a negative delta S. So let's take a look at calculating it. You look up on that chart in the Chemistry 2 textbook and you will see the entropy standard values. Same process as what we went through before, just using different units. They are joules per Kelvin mole. So you still have to consider how many moles you have. You have 2 moles of NO2 times 240 joules per Kelvin mole for the NO2. Again, no other product, so we don't have to add it to anything. Minus 1 mole of N2 times 192 joules per Kelvin mole, plus 2 moles of O2 times 205 joules per Kelvin mole. Put that in brackets. Get your sum, and then subtract that from your product of the NO2. You should find that you have negative 122 joules per Kelvin. Since it's negative, it means that entropy is decreasing, that the chaos is decreasing. It means that it's becoming more organized. Should make sense. You went from 3 moles of gas to 2 moles of a gas, and 2 different substances to 1 substance. It got more organized. Alrighty, I want you to find the delta S for the reaction that converts graphite to diamond. You can stop the podcast. You should find that you get negative 4 joules per Kelvin. That means entropy is decreasing and that diamond is more organized than graphite, and indeed it is. Alrighty. So now we're on the third and final part of this triumvirate of energy that involves enthalpy, entropy, and what we know as spontaneity. Spontaneity refers to whether a reaction will happen without outside intervention. It says nothing about how quickly the reaction will occur. It simply tells us whether it will occur or not. And the way we measure spontaneity is by measuring what's known as free energy. Gibbs free energy, Gibbs. Josiah Gibbs was the gentleman who came up with this concept. And G allows us to measure the spontaneity in a reaction by taking delta G, or the change in free energy, equals delta H minus temperature times delta S. Now your units are very specific here. The delta H units were kilojoules once we divided out the moles, but the delta S units were joules per Kelvin. So that means your delta S units need to be changed to kilojoules per Kelvin, and your temperature has to be in Kelvin. So let's take a look at what we can get from calculating delta G. If delta G is positive, it means that energy is being absorbed, that the reaction has to absorb energy to actually go to completion. It means it's a non-spontaneous process. It cannot happen without outside intervention, and that is known as an endergonic reaction. If delta G is negative, it's a spontaneous process. It means that there's so much energy that it can give some away, it can spit some out. And that means that it will happen without outside intervention. It's known as an exergonic reaction. So, I'm going to show you how to find your delta G at 25 degrees Celsius for the same reaction we've been messing with. The N2 plus 2 moles of O2 yields 2 moles of NO2. You know the delta H and you know the delta S. I've given you a temperature of 25 degrees Celsius. You need to convert that temperature to Kelvin, and then you need to plug in and find your delta G, please. You can stop the podcast and then go to the next slide once you come back, and I'll show you your answer. So as you plug in 68 kilojoules, subtract the product of 298 Kelvin and negative 0.122 kilojoules per Kelvin, you'll get 104 kilojoules. That means the reaction is endergonic. It means it will not happen without outside intervention. So to get nitrogen and oxygen gases to turn into nitrogen dioxide gases, we have to supply energy, is how we translate that. If you find the delta G of the reaction that converts graphite to diamond at 100 degrees Celsius, state whether it's spontaneous or not. Well, I hope you can tell me that this one is going to be non-spontaneous. Think about that. Is your pencil lead going to turn into diamond at 100 degrees Celsius? No, silly. Think about it. Once you've worked it out, you should get 3.49 kilojoules. It's positive. It means that it will not happen without outside intervention. Okay, here you have some more practice. So just write down these next two problems and a couple of slides worth on this number 6 since it's a Hess's law problem. Just stop the podcast, restart it as you need to see the next slide. On this next slide, you see your elementary steps, and I've given you the delta H of each. Pay attention to your phases. And stop the podcast and write down. Once you start back, you'll get number 7, which is your last practice problem. And this one is going to, be a doozy. Yep, you're going to have one like this on a quiz, so get used to it. Stop, write down your problem. And on the next slide, you'll get your answers. Okay, and here are your answers to numbers 6 and 7. So that wraps up what we're going to do for right now with thermodynamics. Oh yeah, it's a lot of fun stuff. Very practical stuff, I hope you've found. And I hope you've enjoyed the podcast and the kitties in the background and the crashing whatever. I'll have to go see what they made fall. And we will have fun practicing this stuff. I'll have a couple of practice sheets, I believe, on my practice work site. So may I enlighten you with thermodynamics. Enjoy. I certainly have fun making these podcasts and having the kitties around me. Bye.